Okay, it's recording now. I see this little button here. All right, so let's go. I was talking about the water cycle then, starting with the evaporation. I had mentioned what evaporates from the surface of water, where it's the oceans or lakes or even rivers. What evaporates is basically pure H2O, all right? Just like when you boil water, when we boil water on the stove, the water vapor that comes out, that goes into gas, is basically just H2O, which leaves the minerals back in the ocean itself, all right? In fact, that's what's happening to the Dead Sea there. Remember the first source looked at evolution, and we saw that the culture part of the theory oxygen. So the mass of that molecule of water is slowed down. So what's the gravity of the itself? Another density that we have actually by volume, which is what? The core, the core. Solid, mostly iron, solid iron with a rather metal. The core is solid, hot, okay? So, and that's why that is the main cause of this effect of gravity, this pull. Every also has anything that has mass and exerts a gravitational field, if you want. So it's kind of a mystery. Anyway, matter has a attract force, right? But of course, we can call it any name, but it's a mystery. Why do these? It's one of the forces in nature. Why is it objects attraction force? And so molecules start coming, especially tiny molecule of dust that's a nucleus clusters is condensed. So that's actually water condensing, and see it. Earth literally classes condensing back into liquid. The little water droplets become molecules come together. They become heavy because of the density that they're holding, and down the surface. Those get switch charge, right, to mass. They now as liquid, downward. We cover absolutely at least determine weather patterns of the Earth in a generally on the plane as happened earthly on the right by the Earth. Earth is up the mountain range, and as it's being pushed up the mountain range, that air, warm, humid air, is cooling down. And as it cools down, it condenses again and has more precipitation occurring, all right? So we see this gradual phenomenon of the condensation of water vapor into clouds, and then the clouds being transported by wind mostly toward mountain ranges. On the mountain ranges, these clouds plus other warm, humid air moves up the mountain, cooling as it moves up. And as it cools, it condenses, and then there is precipitation. Now, the interesting thing about precipitation at top of the mountain ranges is that because it is cold up there and could be below 0 Celsius or 32 Fahrenheit, that precipitation will be in the form of snow, which is water crystals. In other words, solid water, all right? So we have evaporation, gas, then condensation into clouds, liquid, and then the precipitation of clouds on top of mountain ranges, generally snow, solid, all right? So you see the 3 states of matter of water going through it in this natural cycle. When that precipitates snow on top of the mountain ranges, then that snow continues to accumulate on top of each other, layers and layers of snow, and water is relatively heavy, okay? So it has a nice specific density there. You pick up a gallon of water, for example, and it feels pretty heavy. So when that snow starts accumulating layer after layer of snowfall on top of mountain ranges, it starts compressing and compressing, all right? if we move that forward into thousands of years and hundreds of thousands of years, all that compressed snow continuously in a frigid environment can form eventually glaciers, all right, which would be, you know, maybe 1 kilometer of depth of height of ice that has been compressed into these glaciers. And so that's why it's very interesting and very informative to do ice cores on glaciers, because you get all the layering, the stratification of snowfall over periods of cycles of years and years and years. And of course, that snowfall is not without contaminants. So it will pick up also the dust and the pollen and whatever is in the atmosphere at that time and that year, that cycle, and deposit it in the ice core. And these layers of ice also happen at the poles, at both poles, the North and the South Pole. So that's why it's an ongoing activity of geologists and hydrologists and biologists doing these ice cores and looking at the layers and layers of accumulated snow and compressed snow there with all its contaminants to tell indirectly, more or less, how the atmosphere was at that time. The amount of CO2, the amount of other gases also that trap in micro bubbles. They trap into the layers of snow that get crushed into ice. And other minerals, even some organic material, pollen and so forth, a lot of stuff that flies, that is flying in the atmosphere, okay? All right, so as that snow deposits there, eventually it will have, it will start melting at the edge, at the lower edge, and that melting, I'll come to you, Marie, in a minute, all right? That ice that is melting is going to form first little lakes up on the mountain ranges and the mountain tops that are called cirques. Cirques, those are the first little lakes that form as accumulated snowfall that melts, all right? And now we have back to liquid water, and those cirques then percolate down through the rock and form rivers eventually. Rivers on the outside, but also water that filters into the rock, into the mountain and down from the inside. And that's that water that percolates through the soil of the mountain and through the rock of the mountain down at the microscopic level will form internal streams, internal, what's the word that I'm looking for? Springs, all right. Well, the spring itself is where the water manifests outside, but underground water. So not just the rivers that we see on the outside on the surface, but there's also underground water that is moving in through the mountain down toward the valley, and all that water on the outside of the mountain and on the inside of the mountain is picking up minerals. Okay, it's mineralizing little by little. Okay, stop there for a moment. Marie, you had a question or comment?
Yes. So you were explaining that with the snow over time, it could after they all accumulate, they can turn into glaciers over years to show what's been going on with that cycle. So
Yeah.
then my question is, are we ever going to not have glaciers? How the scientists are saying that like the polar ice caps are melting and you know, the sea level is rising because of
Right.
that. So are we never like are we ever gonna not have like, you know, ice caps or glaciers if the world keeps on going, the earth keeps on going into this cycle?
Right. There's a general trend where we're heading in that trend now. I'm going to give you a little short answer because we'll pick up this theme again in a couple of lectures when we look at the whole issue of global warming, okay? It's within the context of climate change and global warming. So we'll go into more detail, but for now, the short answer is that we're heading generally toward a tropicalization of the Earth. So we're gradually losing natural ice on Earth, and let's say the major natural ice on Earth, of course, the major biggest one is Antarctica. And then the next biggest one is the Arctic, Arctic Circle, which we know basically is an ice cube floating on top of the Arctic Ocean. Then the next one from there in size and volume is going to be Greenland, which is mostly covered with ice, maybe about half a mile of ice on top of it, okay? And then the glaciers, and the glaciers are in large mountain ranges. For example, there may be some glaciers in the Andes in South America. There are glaciers in the Rockies, especially up in the Alaska area. There may be some glaciers still left in the Alps, which is in Europe, a mountain range, and then the Himalayas, of course, with the largest mountain range between India and Tibet and China. But all of those glaciers that we have on the top of mountain ranges throughout the world are gradually receding. They are melting right now, so we can say in general that we're heading toward a tropicalization of the Earth, all right? And the big question, especially at the bioethics level, is what percentage of that tropicalization is anthropogenic, in other words, is due to human cause, mostly by the CO2 emission of fossil fuel burning. So we'll get to that big complex question in a couple of lectures and to see detail, all right? First, I am interested for you to understand the carbon cycle, especially. I'm just going to anticipate here for a moment so you can see it. Right? Come on, computer. There, we're going to cover this in a few minutes, the carbon cycle and the net increase in CO2 on Earth, all right? So hold on, we'll get to that question in greater detail. But generally, we can say right now we are heading toward tropicalization. However, there are these natural cycles that I talked about, and I'll pick up in greater detail again in a couple of lectures, where we have had evidence of at least 4 tropicalized Earth and 4 winterized, total ice caps, winterized Earth. All right? Okay. Radioactive, we could trace hypothetically a single on the outside okay, but water in aquifer has mostly iron, most about so generally into the aquifer. It's very easy. It's sulfur smell, rotten smell. A lot of iron also because it be too for the case. Lots of water filters, filtering too, water treatment way back in the East when teaching, I was teaching biology, water plant on 7th Avenue. I guess in the sunset somewhere around Jack or I familiar with the kids. I was fascinated with soil because what is known as hard water. So pH is 5.5% neutral, okay? And the higher the more acidic the water is, more basic, more cations, more positives and others. And so this it's softened, and so it's softened, it's pulled out of silica and softened down to about 1.5, if I remember years ago data. With that, there are different plants that have shown how the water is softened down to it's from the
I don't have the but I'll tell you that we go in solution that we had on the more to the coast and also and we lower that column
for the split and the again, we have no in state which taps down the volume of the lake, the natural volume for the ground to push out. And on agriculture, your urbanization identifies the high density in the state, South Florida population, there's humans, right? Then all lots of all the showers, all the water that we use from the faucet, etc., all the tap water, on the meter, the water, all it is, Lake Okeechobee, from the rivers that flow out of it, or the canals that have been drained, or the Everglades, which is a reservoir just south of the lake, I forgot to mention, the Everglades can be seen as an extremely shallow lake, if you will, because it has a layer of fresh water on top of it, about maybe 3, 4, 5 inches of water. And that is really the source of for all the urbanization that is occurring. We have there basically, otherwise we will be on demise. Sorry, come in.
To add that the supplement the surface is taking aiming at improving that process by storing the flow through the soup. The idea is to bring our closer to this portion on the eastern or cities out that's depleted on the wells. So restore that flow through the different culverts and passes underneath the bridges. So the water moves to the water conservation areas that the state has closer to the turnpike. It should improve that supply. And again, with better conservation of water, citizens being minded, that is a precious resources and we're running a deficit right now, we can kind of offset the actual, let's say, the diminishing from the salt intrusion that we're experiencing.
Right. So Everglades restoration, it's a dynamic, delicate, complex balance. But us, being the human species, the only ones with a brain, capacity enough to understand what we're doing and the cycles and the damage that we're doing, then we have to basically act responsibly. I want to hold off a little bit also because in a couple of lectures we'll get into population density, right, globally and locally, and these issues will come up again because right now I'm basically just layering out first the abiotic factors, if you notice, with the geosphere, hydrosphere, and atmosphere, now cycles, and then we'll layer up on top of that the biotic factors, and the most significant biotic factor on the world by impact, of course, the human factor. All right, so you can see already on the horizon the complex topics that are coming up. Marie, yes?
Yes, so since Luis was mentioning that they're restoring the Everglades to have the water flow closer to the eastern side of Florida, where we're at. So is that gonna kind of help with I don't know if it's a correlation between like red tide. So if we have more fresh water, is that gonna help with the red tide that we're experiencing, or is that like two different separate things?
No, the red tides are a different phenomenon. The red tides are mostly algae blooms on the ocean coast, and they have to do more with, it does have to do with warming and a little pollution, but it has to do mostly with stagnant water that gets warmer than natural. And because there's also a dynamic balance of plants and animals in the ocean and the plankton and so forth. And when that balance is broken, then some species that are very successful at reproducing fast and taking advantage of a window of opportunity, if you will, they will do that. And within a few hours, they will duplicate and multiplicate their volume, their density exponentially. And those are the algae blooms. And it happens with these mostly red algae that can be toxic. All right, but it's a different phenomenon. It is associated, could be associated with contamination indirectly because of the warming of the surface of the ocean. But it also has to do with currents and circulation, water circulation of the ocean itself, different from the water flow that we're talking about here of this evaporation and precipitation, okay?
Want me to say something, Father?
Yep,
okay.
Go ahead, Luis.
Well, I was gonna say that project, the Everglades Restoration Project, one of the phases is to, that the Army Corps stop flooding the Caloosahatchee River with the load of, highly, how do you say that, eutrophication waters in the lake from agriculture that is part of the source of that red tide that we have on the West Coast.
It is. Is it because of the sediment runoff, because of nitrogen and phosphate?
Right, in part because of it. So the idea is to create some temporary reservoirs south of the lake, and that they can use like oxidation lagoons, and there's no need to flood, to open the gates whenever there's some flooding risk into the river, and sending that big flush plume towards the river that ends up in the shallow Gulf coastline. And therefore,
okay. All right, so there is a tie then, bottom line, there is a tie between the contamination, mostly, like you mentioned, agriculture, with adding extra phosphates and nitrates to the earth, to the soil, for nutrients of the plants. And eventually those phosphates and nitrates tend to run off and get into the groundwater and also the rivers, and will go to the shoreline. So yes, I take it back. That could be a source. Those extra nutrients that these algae receive could cause an algae bloom. Mm-hmm.
Wow.
Yeah. It could, yeah. So, and that's on the side of agriculture, mostly phosphates and nitrates.
Thank you.
Okay. Let's move forward. We'll get to phosphates and nitrates in a minute. It's part of the cycles here, especially nitrates. But before that, I want to look at the other big one, which is the carbon cycle. And with this carbon dioxide, okay, which is here, the good old CO2. So first, let's understand this natural cycle of carbon in nature, okay, in living organisms, which is a back and forth between cellular respiration and photosynthesis, all right? Photosynthesis and cellular respiration. It's a back and forth here because plants, through photosynthesis, plants being illustrated in green here, through the process of photosynthesis, generate glucose and oxygen, all right? They generate glucose and oxygen. To do that, they take water and CO2, carbon dioxide. So let's look at a plant for now. Where does a plant get its water? From the root system in liquid form. Yeah, from the root system in liquid form, the root hairs in the soil. And together with that water will also come some nutrients, right? Some minerals that are dissolved in that water. But the main source of water for the plant is going to be liquid water in the soil through the root system. Okay, how about the CO2? CO2 in its natural state is going to be, it's a gas, and therefore it's in the atmosphere. That, remember when we saw the atmosphere, that we were left with a 1% of trace gases after mostly nitrogen, 75%, 3/4 of the atmosphere being diatomic nitrogen, gas nitrogen, and then think about 16% more or less, almost 1/5 of the atmosphere oxygen. Then we get into trace elements, right, which was about 1%, and most of those trace elements is CO2, all right? About 90-something% of that 1% is CO2. That's the CO2 that plants use. So you can imagine it's a minute amount of CO2 in the atmosphere to begin with, and that naturally is being absorbed by plants, combined the CO2 with the oxygen to make this molecule, this wonder molecule of glucose, which is a high energy carbohydrate, as we know, right? For people watching their diet, carbohydrate, glucose, that's the nourishment that the plants make, and that's why they are producers. They are producers specifically of glucose, of starch, which is many glucose molecules put together, and it is a carbohydrate. As a side product of this reaction of photosynthesis, oxygen is produced. All right, oxygen, diatomic oxygen, O2, 2 atoms of oxygen, which is going to be in a gas state at the normal standard temperature and pressure of the atmosphere. And so that CO2 is going to be released to the atmosphere. by the plant, all right? Through little holes that they have underneath the leaf that are called stomata. So now what happens is the animals come into play, and animals are going to use the glucose as a nourishment, all right? And essentially what we do with the glucose is this process of cellular respiration. Another word for cellular respiration is burning. We're burning the glucose, like you hear burning calories, literally, yeah. And we burn it by putting oxygen to it, all right? Because oxygen is very reactant, and when we add this oxygen to the glucose, we get the reverse reaction of photosynthesis, where we split the glucose molecule. All right, and when we split the glucose molecule, we get energy release for metabolism, for living, for being alive. And the products of burning the glucose with oxygen, the products are going to be water and CO2. Water that will come out of our bodies mostly through urine, as it picks up all the minerals and waste products of the body and is excreted by the kidneys through the bladder, etc. All right. And the CO2 that we exhale, the CO2 that we exhale through our lungs back out into the atmosphere, and every animal is doing this process of cellular respiration, okay? Now, plants are also doing this process because plants are also alive. Plants also need to metabolize, need to respire, okay? So in addition to producing glucose, plants are also burning some of its glucose. It's just that they produce much more glucose than the glucose that they need for living, all right, for metabolizing. But plants also metabolize, and they also are involved in cellular respiration. It's not just animals. The difference is that we only respire. We don't photosynthesize. We meaning the consumers, the animals. And these two reactions, which are really the wonder reactions of nature that keeps nature alive, are done in two little, they're called organelles, cellular organelles, because they're inside the cell. They're microscopic, of course, just like the nucleus of the cell is microscopic. And the chloroplast is the one that does the photosynthesis, all right, in these stacks of discs that it has inside. And the mitochondria are the ones that do the cellular respiration. This is at the cell level, all right, at the level of the cell. So these organelles, they're called organelles because they're equivalent to organs inside the cell, all right? Just like organs in the body have particular functions, organelles inside the cell also have particular functions. Now, for the chloroplast to work properly, to connect these two molecules of CO2 and H2O to make glucose with a side product of oxygen, to do this, the chloroplast needs energy to make these bonds, to break bonds and make bonds, all right, and to produce essentially the high energy molecule of glucose. The chloroplast needs light, or a source of energy, which typically is light energy. And the natural, what's the natural light energy on Earth? The biggest source that we have? The sun, exactly, sunlight, okay? So this light energy, but it can also be simulated with lamps, etc. All right, so chloroplast then from cells, from plant material, take up water from the soil, CO2 from the atmosphere, and through the process of photosynthesis, they generate glucose, which is a high energy carbohydrate, and as a side product, they produce CO2. Animals then take up the glucose by eating the plant or eating animals that ate plants, and we burn, literally, the animals burn the glucose by injecting it with oxygen in a process called respiration, cellular respiration. And by breaking these molecules, the end result is that we're going to produce water that will come out mostly through the urine, and CO2 through our lungs that will go back out into the atmosphere. And by breaking that high energy glucose, we get chemical energy. That chemical energy is transferred into another high energy molecule of the cell, which is called the ATP, the adenosine triphosphate. And adenosine triphosphate is basically, you can think of little tiny molecular batteries that we have, high energy batteries that we have in our cells. And those molecules, those ATPs, allow for metabolism. Metabolism, which is body functioning, okay, cellular functioning, organ functioning, wherever energy is needed for a chemical reaction, ATPs are supplied, they supply the energy for those chemical reactions to occur. All right, so here is looking at it in the chemical way. This is called a redox reaction. Redox is a contraction of reduction and oxidation. So the ox is for oxidation, right? Which is adding oxygen, oxidizing. Think of rust, think of a piece of metal, think of a piece of iron, not steel, but iron. And you expose the iron to the atmosphere and it will rust, right? It will become reddish brown because that iron is reacting with oxygen and is forming iron oxide, otherwise known as rust, which is reddish brown in color. And that's also what makes our red blood cells red, is the iron, that is the oxygen that is added to the core of iron in the RBC and gives it that reddish color. All right, so that's the oxygen part, is the oxidation, all right? The rusting of the glucose molecule. And the opposite, so here's photosynthesis, that would be cellular respiration, is adding oxygen to glucose through cellular respiration to make water and carbon dioxide, and we get out of it this energy, which is not light energy, which, because we don't glow, right? Naturally, animals don't glow, rather, there is bioluminescence, but that's a different story. The energy that we get is chemical energy in the form of ATPs, adenosine triphosphate, don't worry about it for now. And also we release heat, the heat that will dissipate out through the body, and the heat that makes us also warm-blooded, right? That we maintain part of the heat in our bodies, again, to maintain metabolism. So here's the chemical, the stick molecule, the stick shape of glucose. You can see it's a 6-carbon ring. All right, 6 carbon, but 1 carbon is off the ring. You notice it's 6 carbons, but 1 carbon is off the ring. Too much detail, don't worry about it. The point is that these carbon-carbon molecule, the carbon-carbon bonds, all right, the carbon-carbon bonds are known as covalent bonds. It's one of the 3 types of basic bonds in nature. And these bonds are high energy bonds, and that's where the chemical energy is stored. All right, in these high energy bonds, the covalent bonds. So when that bond is broken by enzymes, then that energy is released and is trapped into these ATPs, into the phosphate arm of the molecule. All right, so that's the respiration in kind of molecular or atomic detail. Then by way of the plant, so photosynthesis, the reverse reaction occurs, the reverse reaction. Water is combined with carbon dioxide to make the glucose molecule, and there's an extra oxygen left over. There are extra oxygens left over, and so those oxygens just pair up with each other. They like to be in a diatomic, in a divalent stability, all right, gas, but stable, and that's O2. And so to balance the equation for every single chemical reaction of photosynthesis, there are 6 oxygen molecules produced of diatomic oxygen. Okay, that's the photosynthesis. For this reaction to occur, it needs an energy source, which in plants, in nature, typically is solar energy or light energy, right? And this, because it is opposite to an oxidation reaction, it is opposite, it is adding okay, so it's producing oxygen by combining water and CO2. It's called a reduction reaction, okay? It is reduced. The water is reduced with the CO2, with the carbon dioxide, to make the glucose and the oxygen. So that's called a reduction reaction, okay? And so when we combine the two together, we get this redox, which is in a balanced state. Photosynthesis occurring one way, cellular respiration occurring the other way, and there's a balance in nature. And one key element in this balance is the carbon, right? So you see this carbon on CO2 will become this carbon in the glucose. all right, and back and forth, back and forth. When that glucose is burnt up, the CO2 is released. When the CO2 is trapped and reduced with water, it becomes the glucose. It's the core, the skeleton, the ring forms the ring of the glucose, right? So that's the carbon cycle in a chemical way. Let's look at it in nature for a moment with the organisms and also abiotic factors like volcanic activity or geological activity that releases CO2. So in general, the arrows here in red is CO2 being produced, and the blue is CO2 being sunk, being absorbed, carbon being absorbed and retained on the earth, all right? Either by plants, animals, or soil, where most of it is sedimented into, deposited into the crust of the earth itself. Some of it is also dissolved in water, all right? But this carbon sinking is absorbing CO2 and literally trapping it into the earth, which has a cooling effect on the atmosphere. Whereas the release of CO2 into the atmosphere as gas has a heating effect. Why? Because just like water, CO2 is also retains heat. Retains heat, retains in fact a lot of heat, and it causes a greenhouse effect. So it's known as a greenhouse gas. Greenhouse because, you know, the houses up north with the winter, or in the southern hemisphere further south in the temperate toward the cold regions, if you make a house of glass in the winter time, light comes through the glass, it bounces off inside the glass house, and part of the bouncing around is that part of that light energy becomes heat energy. And then other part of the light still stays as light. The light that bounces off the inside of the house will go through the glass, will go back out, all right? But the heat gets trapped inside the glass house. And so it is warmer inside a glass house in the winter in a cold environment. And that makes for a greenhouse. Why a greenhouse? Because then you can put plants in there that will live through the winter, even if it's snowing outside, because of the trapped heat. All right, and they're called greenhouses because they have plants inside, but they have a higher heat inside. Okay, so naturally, we can get the same effect in the atmosphere by the amount of CO2 mostly that's in the atmosphere. And there are other gases, methane and other gases also hold heat in the atmosphere, but this one is the most abundant one. And so if we have an increase in CO2 in the atmosphere, it's going to hold more heat in the atmosphere, and it's going to make the atmosphere warmer. And that's what we mean when we talk about global warming or regional warming, is that basically there's an increase in CO2. So now we need to see what is producing CO2 on Earth, all right? Well, respiration, we know because we just covered it, cellular respiration, all right? The oxidation reaction of glucose is going to produce CO2 as a byproduct. We cannot help it. All plants, all animals, and all bacteria have to respire. They have to metabolize. Okay, so this CO2 is being produced in nature over eons of years, and it's in a balanced state. In addition to the CO2 that is produced by living creatures, right? Whether it's on land or in the water, because fish and algae and everything that's in the ocean, including the plankton, also is respiring, is metabolizing, is also producing CO2. In addition to that source of CO2, there's also abiotic sources of CO2, either from geological activity, like a volcano, which is pretty drastic. It puts out quite a bit of CO2. I remember when Mount Helen exploded there, I guess back in the 80s or 90s on the west coast of the US, with that cloud of smoke went so high, so fast, that within 24 hours it had gone around the world, had gone around the entire world, because it went up into the stratosphere, okay? And in one rotation of the Earth, that cloud of smoke had moved throughout the whole Earth. Okay, so that is fairly significant, much more significant earlier in geologic time when the crust was still forming and the plates were moving much more. Remember Pangaea, and then the breaking up, the Gondwanaland, and then the other Laurasia, and then all the, eventually will be the 7 plates moving around. Okay, so a lot of geologic activity there. To this day, the Ring of Fire around the Pacific Rim, all coasts are still volcanically active and so forth. So there's a significant amount of CO2 coming from there. Other fires, forest fires, natural forest fires throughout the world occur, all right, just natural, not human made, but mostly lightning striking and causing a fire will generate combustion. These are all sources, natural sources of CO2 in the atmosphere that typically are being counterbalanced by photosynthesis and the sinking, also erosion and deposition through rain that picks up CO2 from the atmosphere, sinking it into mostly the oceans and soil. But then there is the extra, which is the burning of fossil fuels, because no other creature goes into the soil, puts out fossil fuels in its 3 forms, which is coal, petroleum, and natural gas, and burns it. No other creature does that except us, mostly in industry, and then we produce an extra source of CO2 here. The 1 species of the 2 million that exist here or that have been classified, we're the only ones who do this, all right? Taking out sunk carbon that is sunk into, again, coal, petroleum or natural gas, and we pull it out and we burn it and we get a lot of energy out of that. Of course, it's running basically the industry for the past about 250 years since the Industrial Revolution, more or less, with the invention of the steam engine, which requires water to boil, heating up the water using the fossil fuels. Okay. Let's look at this cycle now. Let's look at some numbers, all right? In gigatons, this is what is known as a budget, the annual carbon budget, all right? Annual carbon budget, the yearly budget of carbon. And it's going to be measured in gigatons. Gigaton is 10 to the 9 metric tons, okay? So 3, 6, 9 zeros. That's a gigaton, all right? Million will be here, billion will be here, trillion, gigaton, a metric ton. And 1 metric ton is 1,000 kilos of CO2. It's a gas, yes, but it does weigh, right? We put it into a tank and that tank will weigh more full than empty, a gas tank, because the gas weighs. Otherwise it wouldn't react to gravity. Anyway, so 1 metric ton is 1,000 kilos of CO2 gas, right? So you can get a feel for what a gigaton is 10 to the 9 metric tons of CO2. So follow the green numbers first, which are the natural numbers, and we can start from the arrows going up. For example, plant respiration. There's much more plant material on Earth than there is animal material, right? Much more vegetation than there are animals. So by far, the larger amount of CO2 that is released into the atmosphere naturally comes from plant respiration, from plant cellular respiration, burning up their own glucose, all right? A little bit of the much glucose that they produce. So that makes up, on an annual basis, throughout the whole world, approximately 60 gigatons. It's a stable number, all right? It's a stable number, has been figured out, approximately. So that's 60 gigatons. Plus another 60 gigatons of CO2 that are produced naturally on Earth, excluding humans, just from microbial respiration and decomposition. So decomposition is also a burning process. When decomposers, when they chew up organic material, one of the side products, because it is metabolism, they're metabolizing organic material, they produce CO2, okay? And so microbial and decomposition of organic material on Earth produces another 60 gigatons of CO2 annually. So that's 120 right there, okay? The ocean also produces about 90 gigatons of CO2. Part of this is respiration. Another part is just CO2 that was dissolved in the water column that at the surface gets to escape because it breaks through the surface tension and so forth and escapes into the atmosphere. So about another 90 gigatons of CO2 are naturally produced on the oceans, okay, on an annual basis. But now let's look at some other down arrows, still staying on the green and the blue numbers. Let's go back to Earth. Photosynthesis absorbs annually about 120 gigatons on the surface of the Earth, on the land side of Earth, all right? About 120 gigatons. How nice, how convenient, because 60 of cellular respiration from plants and 60 from microbial respiration on soil adds to 120, which is being sunk, is being absorbed, sucked up by photosynthesis, and therefore sunk by way of organic material, all right? And this organic material is trapped, if you will, into the glucose molecule, the starch, also other molecules, the carbohydrates in general, like cellulose, for example, that makes up the plant itself. And some of it also gets sunk into the soil, all right? So just on the natural numbers, 60 plus 60 release, 120 absorbed, there's a net zero balance before looking at the red numbers, okay? On land. On the oceans, pretty much the same. Even though there's 90 being produced of CO2, there is 90 gigatons being absorbed mostly by the phytoplankton, which is also photosynthesis. Now, plankton is microscopic organisms in the upper layers, upper foot, more or less, of the ocean, okay? And sometimes the greatest density is in the upper inch of the ocean, a couple of inches. So that plankton is subdivided into plant or animal plankton, and the plant plankton is called phytoplankton, and the animal plankton is called zooplankton. But the producer on the ocean is the phytoplankton, all right? And so you can think of that thin layer of phytoplankton on the surface of every ocean, which is 3/4 of the surface of the entire Earth. You can think of it as a huge lawn, a microscopic lawn that is extremely effective in sucking up CO2 because it is photosynthesizing. That's the phytoplankton. Of course, very nearby, within a few microns, are going to be zooplankton that are eating up the phytoplankton. So those are the primary consumers, the zooplankton that feeds on the phytoplankton, and then other animals feed on the zooplankton and so forth. You get the whole food chain and the food pyramid, okay? But basically, this phytoplankton absorbs about 90 gigatons of CO2 annually on the surface of the ocean, which is the 90 that was produced by the process of oceanic cellular respiration and decomposition going on there, okay? So we have a net balance here of 0, 90 produced, 90 absorbed. It's a net balance of 0 naturally. However, when we add the human species on top of the surface of the Earth and we add the industrialization that has been going on, like I say, mostly since the Industrial Revolution, close to 300 years ago now, what happens is that we are producing an extra 9 gigatons. Not a big deal when you compare it to the other numbers. You know, it's 1 order of magnitude less. 9 gigatons approximately of fossil fuel burning. Also cement produces CO2 in the process, and other man-made CO2, okay? These 9 gigatons get distributed on land. They add about 3 of these 9 gigatons. About 3 gigatons are absorbed also in photosynthesis. So photosynthesis absorbs extra, actually absorbs 123 gigatons, right? Excess of the output of CO2 on land. So of the 9, 3 get absorbed through photosynthesis on land and sunk into the soil, right? Or into the organic material of the plant itself. Plus 4 from the 9, 4 get absorbed by the oceans. Sorry, 2, I'm sorry, here, 2 gigatons, all right? According to this estimation, 2 gigatons of this 9 get absorbed by the ocean phytoplankton. So we see that the phytoplankton also has a capacity to absorb excess, not just 90, but 92. These 2 come from our production of CO2. Okay, so we got 3 over here, we got 2 over here, makes 5. 3 plus 2 make 5. But to the 9 leaves 4, net 4 increase. Okay, so this is the deal. This is the anthropogenic CO2 produced on an annual basis of CO2 into the atmosphere is a net of about 4. So about half, a little less than half of the CO2 that we are producing through burning of fossil fuels is staying in the atmosphere, and the other half is being absorbed by the excess photosynthesis of either land or ocean plants or phytoplankton. So this is the issue here. This excess 4 gigatons that is accumulating over the years, over the decades now, and it's gradually heating up the atmosphere, okay? That's by the numbers. Okay, so that's the concern here. That's the concern. So that's why if we act responsibly and we start looking at alternative fuels that are not fossil fuel, if we manage to bring this number 9 down, for example, if we bring it down to 5, we're good to go. If we cut it in half, essentially, you know, we're good to go because the photosynthesis between land and ocean will take care of about half of the 9. But the other half is too much. It's just too much, okay, by the numbers. So that's what you have to deal with. All right, let me move on. Let's look at another cycle, which is the oxygen cycle. In nature, again, oxygen in the atmosphere is known as diatomic oxygen, oxygen gas, which it just the 2 atoms of oxygen like to hang around with each other because they stabilize each other. The valences stabilize. And so it's called diatomic, right? Just like nitrogen, N2, hydrogen, H2, oxygen, O2, all right? Diatomic, 2 atoms, gas. And then in this oxygen cycle, we have to add water and CO2 because guess what? You see, there's 1 oxygen trapped in water and there are 2 oxygens trapped in CO2, right, in carbon dioxide. And these, we just talked about the water cycle and the CO2 cycle, so that's part of the oxygen cycle. In addition to the water cycle and the CO2 cycle where oxygen is trapped in there, we also have just oxygen cycle, naturally, diatomic oxygen. So I don't know, the arrows are going up or down. The oxygen cycle is a little more complicated because sometimes oxygen is trapped in water, which will move through the water cycle. Sometimes oxygen is trapped in CO2, which will move then through the CO2 cycle that we just saw, all right? And then there is also atmospheric oxygen that is being used for cellular respiration. The one in black is oxygen, is atomic oxygen that is being used either by cellular respiration from plants and animals or by combustion or either combustion of plant material, wood, etc., or is by the fossil fuel combustion, and all that is producing CO2, which is then going to be absorbed by the plants through photosynthesis and recycled back into oxygen. So you can see that the oxygen has several different cycles going on. has the natural water cycle going on, has the CO2 water cycle, which ties it into cellular respiration and photosynthesis. And then there's also the fossil fuel burning or natural combustion that is also going to trap oxygen and trap it into CO2, okay? So you can see that the oxygen cycle as such can be subdivided into just diatomic oxygen gas, or trapped in water, or trapped in carbon dioxide. Let me move forward. A couple more cycles, then we'll break. Take a break. Nitrogen. There's another major element that is cycling in the atmosphere on Earth naturally. All right. So at the biochemical level, briefly, we can start maybe here with a protein. So for the four major groups of organic molecules, proteins, lipids, carbohydrates, and nucleic acids. Nucleic acids are what? DNA and RNA, right? So proteins, lipids, carbohydrates, and the nucleic acids are the four major groups of what we know as organic molecules. All living organisms are made up of these four large major molecule groups. So we can look at proteins, and these proteins decay, they break down, they decompose, and we excrete them through the urine, which turns into ammonia and goes into the soil typically. And in the soil, bacteria, they're called nitrifying bacteria. They turn ammonia into nitrates, first nitrites and then nitrates, and then the nitrates can be absorbed by plants. Some of it goes back into the atmosphere, others are absorbed by plants, nitrogen fixing bacteria, and they form the building blocks of proteins, which are known as amino acids. All right, so let's look at amino acids. There are about 20 amino acids that occur naturally, all right, in nature, about 20 amino acids, and they're like intermediate molecules. They have this configuration generally, and then there are carbons here, oxygens, there's sulfur, and then there's this nitrogen. There can be a chain here of different molecules. This will be like the head of the amino acid, and this particular part, they're called amino acids because they have an amine group, and the amine group is one nitrogen and two hydrogens, and then a covalent bond with carbon. This nitrogen is the one of interest, right? Because all amino acids have this configuration here. They have a nitrogen balanced by two oxygens and connected to a carbon. And like I mentioned, there are about 20 different amino acids in nature. What changes is this chain here, all right? But the head of it is always this. And these amino acids link up in a chain, all right? Like wagons to a train, more or less, wagons to a train. And you can see them here. When they link up like that, and they turn into a string or a line or a chain, this is called a polypeptide. Polypeptide is an intermediate molecule between amino acids and the actual functional protein, all right? And these polypeptides come in two basic shapes, either alpha helices, it's a helix like this, all right? It's a winding effect, like a coil, they call alpha helixes, or beta sheets. Beta sheets is they form kind of flat structures like this, the polypeptide. These are the two major configurations of the polypeptides, three-dimensionally, right? Once we go beyond just the string of amino acids, they can either form coils or flat sheets, right? And when when polypeptides come together, they come together to form three-dimensional complex structures known as a tertiary structure. These structures, again, come together typically in multiple fashion of their own configuration, multiple functions, and they make finally what is known as the quaternary structure. The quaternary structure is the actual functional protein, all right? Give you an example in a minute where you can put it in context. And here's the quaternary structure, which is the actual functional protein, all right? So this one in particular is, for example, this could be hemoglobin. Hemoglobin, which is at the center of a red blood cell, an RBC. At the very core here would be an iron, Fe, one iron molecule, one iron atom that is at the core, right, at the center, and is holding this molecule together. And that's the iron that gets oxidized, that gets rusted with O2. So that's how the oxygen is transported in the body, literally, by this iron becoming iron oxide, FeO2, and it gets transported from the lungs to the tissue, where the oxygen then is absorbed by the cells for the process of burning glucose. So there's another cellular oxygen cycle there that is occurring from the lungs to the tissue, burning the glucose and then being trapped into the CO2 molecule, which is then released back from the tissue out through the bloodstream to the lungs, and we exhale then that oxygen in the form of CO2. But I want to go back to this molecule, which is hemoglobin. You notice it has 4 subunits. Each one of these 4 subunits in color, the red, the orange, the blue, and the green, they're the same molecule, all right, but twisted around in a different shape. Sorry, the shape is the same, but the way it's put together around the iron, okay, we'll have this particular configuration, 3-dimensional, called the quaternary structure. Each one of these 4 that makes the hemoglobin, each one of these 4 is a subunit that is known as a myoglobin. Myoglobin. So the myoglobin is the polypeptides coming together into this basic structure, this basic 3-dimensional structure, if you will. That's the myoglobin. And 4 of these coming together around a core of iron form the actual hemoglobin, all right? So 4 subunits of myoglobin form 1 hemoglobin. And this is the actual functional protein itself. It's known as a protein complex. The myoglobin itself is a combination of helices, of coils, and sheets, as you can see here. So here's one coil, here's another coil, and here are sheets that are interacting, and they come from the polypeptide structure of alpha helices or beta sheets, right? And these helices or sheets themselves are made up of chains, links, strings of amino acids. So we can go all the way from the primary structure, which is the actual string, all right, to the secondary structure of the polypeptide, the tertiary structure of particular specific polypeptides that will then combine with each other to form the actual functional protein at the quaternary structure. At the core of all this is nitrogen. So nitrogens are essential for proteins, and they cycle in nature, all right, between plants and animals and the atmosphere and the soil in this kind of fashion. So let's look at it here. This would be in nature. We can start with atmospheric nitrogen, for example, which I mentioned is N2, which is 3/4 of the atmosphere, of the gas that we're breathing in and out. That is inert. We don't do anything with this nitrogen, okay? Rather, that gets fixed into the soil by these bacteria that are called nitrogen-fixing bacteria. And these bacteria live mostly in legumes, in the root system of plants that produce beans, all right? So think of any beans that you like or don't like. These are known as legumes, and these legumes are known for having these little nodules on the root system that are full of nitrogen-fixing bacteria. What these bacteria do is precisely they transform that bacteria, the nitrogen, either atmospheric nitrogen into ammonium, all right? And then other bacteria continue the process into nitrites, which then become nitrates, and the nitrates can be absorbed by the plant through assimilation, right? Dissolved in water as the root hairs absorb that water with the nitrates, which are going to be nutrients for the plant. Nutrients for the plant, basically for plants to make their proteins, because they need the nitrogen, this nitrogen in the NO2 and NO3, to make their amino acids, and to, from those amino acids, the polypeptides, and for the polypeptides, the actual functional proteins that are needed for the metabolism of the plant, okay? Now, the plants also die, and when they die, they're going to be chewed up by decomposers. They're going to be broken down by decomposers, and these decomposers also contribute to the ammonium on the soil, which then is taken up by the bacteria into nitrates, nitrates, and the cycle continues. These decomposers are mostly fungi and other types of bacteria also that break down all organic material. Not only plants, but also animals who die and decompose by the fungi and the bacteria, again, into ammonium, and the cycle continues here, okay? There are other bacteria who are denitrifying bacteria, and these take nitrates and essentially strip off the oxygen, so that then the nitrate will become gaseous and diatomic and release to the atmosphere, and that contributes to that large percentage of the nitrogen that is gas, atmospheric nitrogen. So we have these cycles going on of nitrogen, all right? And it is, again, essential for life, mostly for the proteins that are made in life and then that are used by plants and animals for living. Okay, which, by the way, also fungi and bacteria have proteins, but particularly fungi. Fungi are mostly protein, all right? So they also need that nitrogen to make their own polypeptides and functional proteins. Okay, backing out to the big picture now, and if we look at the human body, we can look at the components of the human body by elements. By elements, our body, by weight, is mostly oxygen. A little over half of our body weight is oxygen, right? Just the element oxygen, about 65%. The other, almost 20%, the other fifth of our body is carbon, just elemental. If we were to just put the human body into bags of elements, about 20% of our body, 1/5 of it, more or less, is carbon atoms. Another 10% is hydrogen atoms, right? A lot of hydrogen atoms is just that by volume, by weight, they're so tiny that they weigh very little. And about 3% is nitrogen, elemental nitrogen. So between these four major elements is 95% of our body, right? Oxygen, carbon, nitrogen, and hydrogen. These four elements make up, by weight, elements make up about 95% of our body, okay? Or any body, organic body. The other, more or less, half, 5%, 4%, other elements, all right? So I give you a list here of the other elements. For example, phosphorus, which has its own cycle, phosphates and phosphoric acid and so forth that circulate in metabolism. Sulfur also is needed for life, so phosphorus, sulfur, in different substances that we have in the body. And then come the minerals, calcium, potassium, sodium, chlorine, magnesium, right? They also make up part of the 4%, these minerals, the electrolytes that we need for living. And then finally, the trace elements, typically less than 1%, trace elements. We have many other elements in our body and minerals like iron, manganese, iodine, copper, chromium, cobalt, silicon, zinc, boron, etc. Many other elements that are trace elements, and yet they're less than 1% per volume, but necessary for living, particularly keeping glands healthy and so forth. I mean, we've heard of iodine, for example, for the normal functioning of the thyroid and many other metabolic processes, okay? So it's interesting that whereas our bodies are made up mostly by 4 elements, many other elements are also needed in the body for normal functioning. And the same argument can be made for other animals, plants, and fungi and bacteria, all living organisms. Just before the break, which is coming up briefly, I want to mention hydrogen, since I've been talking about hydrogen, but there's also a hydrogen cycle. The problem with the hydrogen cycle is that it's ubiquitous. Now, what do we mean by ubiquitous? Ubiquitous is that it's everywhere. Hydrogen is everywhere, but it's mostly trapped. I mean, there is some in the atmosphere, look at this, but it's a very tiny percentage. Is 0.00005%, okay? So if you turn this percent into parts, you'd have to add 2 more zeros here, okay? So the percentage of the atmosphere that is hydrogen, which is gonna be diatomic hydrogen, H2 gas, right, is 0.00005%. Now, that's a good thing. That's an extremely good thing because hydrogen is highly reactive when it's gas. H2 is highly flammable and tends to explode, as we know from that infamous Hindenburg Zeppelin that came close to, I think it was the launching tower actually, came close to it and exploded in midair, all right, because it was full of hydrogen. So this was the heydays of navigation, and about a century ago, people figured out that hydrogen is lighter than air in general. It tends to go up. That's why we lose hydrogen, right? In the atmosphere, it tends to, is the lightest, it stands to reason because it is the lightest element and therefore is least held by gravity. So being lighter than the general composition of air tends to go up higher. And so if we fill a balloon with hydrogen, it's going to float up, right? And as it floats up, it's also going to expand and eventually will burst the balloon by expansion. And if it doesn't burst it by expansion, it's going to burst it by combustion. If it gets any little tiny static, a little tiny spark, will make it blow up in flames. And that's why also the balloons that used to be filled by hydrogen for parties are now filled by helium, which is inert and doesn't explode like hydrogen does. But that's just the atmosphere. It turns out that most hydrogen is actually trapped in molecules because all the 4 major groups that I mentioned, the carbohydrates, proteins, nucleic acids, and lipids, all of the organic molecules are literally coated by hydrogen. They're coated by hydrogen because hydrogen stabilizes the molecule. It has one free little valence there that can be taken up whenever there is a negative charge somewhere. The hydrogen will balance out that negative charge with a little positivity and literally coat organic molecules. You know, as you can see, all these H's represent hydrogens. And so organic molecules are totally filled and stabilized and balanced by lipids, okay? By hydrogens. So that's why I say ubiquitous, meaning that it's everywhere. The hydrogen cycle is extremely complex, especially in organic material, because it's basically going to follow the cycle of that particular molecule, whether it's a carbohydrate like glucose going through the respiration photosynthesis cycle, or proteins going through the nitrogen cycle. Nucleic acids also get broken down and built up, not to mention lipids, fats, oils, they get broken down and built up in cellular metabolism. Okay, again, I've been talking for almost 3 hours, so I'm gonna stop here for a moment. Let me ask, actually about 2 hours, any questions, comments before we take a little break? No, hopefully you're still there, some of you anyway, and you have been able to listen and absorb some of this, okay?
Thanks.
Yeah, the images were okay, it was clear enough that you can see stuff, yeah?
Yes, way better.
Yes.
Yeah, everything was good.
Super. Okay, so let's take a break now. Let's say I have 11:37. What do you need? 5, 10 minutes? 10 minutes. We'll come back at 11:45. All right.
Okay.
11:45, and we're going to go into the second half, which is going to be human waste, human recycling of trash, and bioremediation. All right, so
so the phosphorus cycle, we're not going to cover.
No, not in detail. It's just too much, and really, my purpose for this was to look at these four major cycles. There's phosphorus cycle, so that is mostly in metabolism. Okay, but no, we're not going to cover it. Just mention it in passing. All right. So a little break here. Pause recording. Okay, hello everyone. Sorry for the delay. Getting started back up again. Okay, so in case you're not back on yet, we'll just pick up on the recording later. Let's move forward now, and we're going to look at human trash production and recycling. How do we go from here? And also bioremediation, trying to correct some of the errors and the damage that has been done to nature. All right. I want to mention, first of all, well, I already mentioned several times that we are the only species that actually produces trash. Everyone else in nature is just recycled, including their own bodies and what little things they build and make. For example, a nest will eventually get broken down, right, by the wind and the rain and so forth, and get recycled. So we're the only ones who actually produce this amount of trash, of stuff that we make and gets left over. And so we can classify the stuff into five major categories, either wood or metal or glass or plastic or electronic parts. And wood includes also paper, cardboard, fiberboard, all that stuff that has mostly a cellulose basis, right? Whereas metals, we know metals all over the place. It would be mostly iron, but also some other metals built in there with alloys and so forth. But again, I would say mostly the key element in metals is going to be iron one way or another. Glass, mostly silica or silicone, all different kinds of bottles, other kind of glassware that gets broken and so forth. Then many different kinds of plastics, right? But the plastics come mostly from petroleum, from fossil fuels. These long molecules, polymers that are used for making different plastics that we use on Earth, and an increasing amount of plastic that is being used on Earth, many different types of plastics. Mm-hmm. Then the electronic parts that also are becoming a waste, part of our trash, and accumulating as we have this built-in obsolescence by industry and having to replace our computers, our phones, our cell phones, and the regular phone, and TVs and radios and all these electronic components. They have to be, well, updated. And so what do we do with the old ones, right? What do we do with the old ones? Okay, let's say that, sticking with this for a while, of the three first categories, we have pretty much been able to recycle this, or at least we have ways of recycling wood products, metal products, and glass products pretty efficiently. All right, pretty efficiently, so that with wood products, we can make other stuff, furniture, and many other stuff, paper, again, recycled, etc. So wood, we can pretty much recycle fairly well, right? Just by itself. Of course, this assumes that these different categories would be isolated from each other, not much contamination. Metals also, we can pretty much recycle, break them down, and re-smelt them into new metal components of all kinds. And also glass. Glass can be recycled, broken down, and grunched and heated up into molten glass again, and reshaped and recycled. One problem is plastics, and another problem is electronic parts for different reasons, okay? Because plastics are these long polymers that tend to last a long time in nature, and they're accumulating at extraordinary rate. If you look at the shoreline of this contaminated beach here, this polluted beach, most of the items here are plastic, because unlike wood, metal, and glass, plastic doesn't break down. It's so synthetic and so artificial that it doesn't break down as easily as wood, metal, or glass. I mean, think of it, an equivalent piece of wood or piece of metal floating on the ocean, any amount of time is going to break down, right, by natural processes, but not plastic. It holds on its shape much, much longer, predictably into the thousands of years, even though we haven't had significant amount of plastic for thousands of years, right? But it's lasting dozens of years now, essentially undisturbed. So we can assume that it will continue like that. Because the things that break down plastic naturally are things like very high heat or high salinity or high ultraviolet, all of which are pretty dangerous and toxic to the human person, okay? So plastics are a big problem, but if we get them clean enough in the recycling, they can be recycled. Eventually, they can be recycled. One that is a big challenge is electronic parts. Old electronic parts, old could be 3 to 5 years, okay? Because again, the built-in obsolescence of not just the software or programs that need to be updated, but also the hardware to handle the software. Think of just the amount of memories that is needed for some of the software to run today in computers. Well, that has to be backed up by an equivalent hardware that can handle all that memory, okay? So the old floppy disk and the old computers get tossed out, the old regular phones get tossed out, replaced. What do we do with all that waste, with all these electronic parts, which have a lot of toxicity in them? Because they have trace metals, they have rare earth metal elements, and they can contaminate. So typically what's happening, mostly from the northern hemisphere and the northwestern hemisphere, the most industrialized nations that use a lot of electronic components in daily living, right? And in industry and in business and in just our regular life. When all that is trashed, it ends up down in the southern hemisphere. It ends up in parts of Africa, sometimes Latin America or Asia, in huge, huge garbage heaps. In other words, we actually sell garbage to other parts of the world, mostly the southern hemisphere, poor countries that buy this trash, right? Or we pay them for taking the trash. But the point is that then these huge garbage heaps made out of electronic components, people go in there. And even though it might be illegal, you can see a fence behind here, it might be illegal, they go in there and they start pulling out whatever little tiny piece of gold or platinum or mercury or whatever is found in those electrical, or copper, for example, copper, which the price of copper keeps going up. You know, and by hand they do that under horrible, horrible conditions, and there is contamination that is occurring to these people who are going into these huge trash mountains, mostly in Africa, but also Asia and perhaps some parts of Latin America, of poor people just living in these trash mountains and trying to make a living out of whatever little component piece of metal they can pull out of there. Mostly, I guess they go for the copper. I guess it's maybe zinc also, or aluminum, anything that they can find that they can sell. all right? So this is a big problem, a source of contamination for more or less in general from the northern hemisphere to the southern hemisphere. Okay, so we don't know about this normally, but it's there. And I don't have a video on it, but I've seen videos. You can look it up on the internet. Okay, let's move to the oceans and look at the gyres, because remember I talked about the 6 large gyres, right? Actually 5, 2 in the Pacific, 2 in the Atlantic, and then the Indian Ocean gyre. 5 huge gyres or current circulation that are somewhat horizontal. There are some minor ones also in other pockets of the world. But one that is particularly significant has become this, what they call the Great Pacific Garbage Patch. The Great Pacific Garbage Patch, which is in the North Pacific Gyre, which is much smaller than the South Pacific Gyre. Well, pretty smaller. And it tends to concentrate. The North Pacific Garbage Gyre tends to concentrate pollution, which is mostly made up of plastics, but much of which we don't see. They're called microplastics and microfibers, and we'll see some videos on that. So let me show you the first video on the Great Pacific Garbage Patch. Here is where I need to go to the optimization of videos, which could make the image fuzzy. So let me try this, optimize for sharing video. And now I need to go to the internet and see how we do with this video. Okay. Close down some sites here. Okay, so let's see. Hopefully this video will show better than the previous times. If by chance it doesn't, you have the links on the PowerPoint, so you can take a look at them on your own also. Okay, so far so good. Before maximizing, I want to make sure that it downloads. This one is under 3 minutes. Most of the videos are 3, 4, 5 minutes. There's one that's a little longer. So let's see how we do. Memory issue. Let's hope it does. Maybe I can close this one. Suspended in the water column, all right, and floating around in the middle of the North Pacific Ocean. And that's how it's known, the Great Pacific Garbage Patch. And it's a phenomenon of our contemporary society, because what's floating there is mostly plastics of all different kinds and shapes that are taking a long time to break down. All right. Now, as I say that, they're also being encrusted by a lot of barnacles and other sea creatures that help in the process of breaking down the plastics. But a lot of it is just suspended in the solution, and they're microscopic, these microbeads and microfibers. All right. And so I want to show you, hopefully, these three little, these little videos will be less heavy. They explain what are these microbeads and microfibers in more detail. Let's take a look. Hope we have better chance with these videos. Okay, it's encouraging. A little faster. Let's see if it actually downloads. Oh, it's the same problem, same process. And okay, let me try to do this to send you, because all the links are in the presentation. So if I send you the presentation, the PowerPoint, you will have all the links there. So let me try to do that through email. Hopefully I can open any. So the link